Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning. It is my pleasure to invite Simon Corman to give a talk here at Microsoft Research. Simon is finishing his PhD at Tel Aviv University under the advisement of Professor Shai Avidan. He was also doing an internship here at Microsoft Research. So, Simon.
Okay, thanks very much for having me. And this is the topic of the talk today, Inverting RANSAC. This is recent work that will appear in CVPR, joint work with Roee Litman, Alex Bronstein, and Shai Avidan. So before I get into details here, I'd like to give the context and just say something about other things I've been doing during my PhD. So the problem I first started looking into is of computing an approximate nearest neighbor field between a pair of images. So that is, you need to find a dense mapping between the entire set of patches of one image and the entire set of patches of the other image. So this is a problem of high complexity because the number of patches in each image is like the number of pixels. So you need to do some approximation here. You probably know of the patch match method that came out in 2009, which really made this task possible in a couple of seconds, I'd say. So we came with this approach, coherency-sensitive hashing, where we incorporate a hashing scheme into this problem, and we managed to do so to find a matching which is more accurate and faster than what patch match can do. Later on, and this is joint work with Eyal here, we looked into the same problem, but when we have the additional information of a depth channel of the image. And we asked ourselves whether we can do a better, so again, just an RGB matching between patches if we're given this additional depth information. And it turned out to be that the answer is yes. We have a way of using the depth information to kind of rectify in some way the patches and reduce the problem to a problem similar to the original one. And as an application, we focus here on single image denoising, and we show that when we use patch-based denoising methods which are fed with our patch matches, we get results that are significantly better than state-of-the-art in single image denoising, but again, compared to methods that do not use depth. So we really managed to show that using depth makes a difference here. And now to, this is I think the main line of my works. And you could put them under this frame of global model detection. So these are 4 different problems. I'll just go through them quickly. So the first one is about template matching under affine transformations. The second one is about finding global rigid symmetries of 3D shapes. The next one is, and this is the topic of today's talk, about registering a pair of images given a set of matching interest points which contain noise and outliers. And finally, there's this work here about depth extension, and it is done by designing a special kind of template matching that is specific for this task. So this is still work in progress. And what is common to all these problems, or the way that we tackle them, is that there is some very large search space in which we want to find a model. And what we show in different ways here is that if you have an understanding of the error function the way it changes across the search space, you can do a kind of an efficient, exhaustive search that gives you global guarantees about the result you obtain. So let me get into this work. So I'd like to start with this very simple canonical example in robust estimation, which is fitting a line to a set of points. So in this case, the line is the model. You can see typically what you have is a set of inlier points. These are the red points, which have some amount of noise around the model. And in addition, you have outlier points. These are the blue ones here. And if we count the number of inliers in this example, we can say that the inlier rate, and we mark it by P star, is, in this case, 8 out of 17. There are 8 inliers out of a total of 17 points. Now, what would be the standard way to find such a model behind a set of points? So you would use kind of solve the problem of maximum consensus maximization. And the standard way to do that is RANSAC. So you're looking for a model that has the highest support of data. So in this case, what does RANSAC do? It's an iterative method. At each iteration, it picks at random a minimal subset of the data that can generate a model. In this case, it picks at random 2 points, looks at the line that goes between them, and measures the amount of support. And how does it do that? It's given an inlier threshold, which we mark by R star, and it counts the number of points within that amount of error. Okay, so this is not a very successful choice. It gives only 2 inliers. But repeating this process, you can get better and better lines, like 4 inliers here. For instance, this line was, so the 2 points that were chosen were actually inliers, but still the line that went through them is not perfect. It's close to the true model, but not there yet. So this gives 5 inliers. And eventually, you might find this, this line that explains the complete set of inliers in this example. Now, our method works in a very different way, and we call it GMD, Global Model Detection. So what we start with is, as I said or suggested before, is we look at a sample of the complete space of solutions. So in this case, we're looking at a set of lines. So for instance, we take this sampling of horizontal lines. We look at different orientations. And once we have this sample of lines, the second step is to directly estimate the inlier rate P star. Okay? Now, assume we've managed to do that, and we somehow know now that P star is 8 out of 17. We can go to the third step, which is to find the best line for this specific inlier rate P star. So we can look at each of the lines in our set. For instance, this line here, we look at the 8 closest points. So, sorry, this would be the 8th closest point, and it gives some amount of error. And we can measure this over the entire set. And I will show that if we return the best line that we found, we have a guarantee on the error that it gives compared to the best line in the continuous space. So this is something we can do, but we go further, and we can employ here a branch and bound scheme, again using these exact guarantees, and actually get as good as an approximation as we want. And we can actually find the optimal line for this specific inlier rate P star. So this is just an example of another line. And finally, we will find this line, which has this error, which is optimal for this P star equals 8 out of 17. So I will talk about the guarantees that allow us to do this. But the main part of this work is actually going back to step 2, which is how do we figure out what the inlier rate P star is. So getting back to step 2, and we notice this very interesting phenomenon here, if we look at this best line for the true P star, what we notice is that the error that it obtains is very rare. And what do I mean by that? I mean that if we look at different lines in the space, it turns out that there are very few lines, or the portion of lines that have an error that is similar to this one is extremely small. Okay, so you can imagine if you take different lines, different orientations or locations, there would be very few lines that get this kind of error for the 8th closest point. But what if we had a wrong estimate of P star? So for instance, if we had an underestimate, like 5 out of 17, so this is actually the best possible line for the 5th point. But here, it turns out that there are many other lines, like these ones here, that have a very that have an error that is very close to the optimal one that I just showed. And these lines are close to the real model, but actually it might even happen that a line like this one, which is very far, can also have a very close error to the optimal one. And if you take an overestimate, like 11 inliers, you have the same behavior. This is maybe the best line for 11, but there are many lines for 11 points that have a similar error. So what we get overall, and this is just an illustration, but this is the behavior we see, is that if we look at the x-axis at different possible inlier rates, and for each one we count the number of, we call them good lines or good models. So good lines are ones that have an error that is not much worse than the best one possible for the specific inlier rate. So we see this kind of behavior. So this curve has a clear minimum at the true inlier rate P star. So we call this our IRE measure. I'll define it more precisely. And we basically compute it for different percentiles and choose the minimum, take P star to be the one with a minimum value.
So to compute the inlier rate for a given line, you find the n closest points, like you find the 8 closest points and then measure the sum of square differences or something?
So we actually work with the distance of the 8th closest point, not the average or anything like that. We just take the percentile of the specific percentile of errors with respect to the model. So in this case, this is just a simple case. It would be the distance of the 8th closest point.
The distance of the 8th closest point.
Right.
Okay. Right. Okay.
Yeah.
So you basically, for a given candidate line, you can just tabulate all of the distances. In essence, sort them if you need to, but maybe you don't need to sort, and just basically compute what the thing is. Okay.
Right. That's exactly what we do. Yes.
Is this curve very sensitive to how densely you're sampling your candidate lines?
So I'll get to that. So we have a theoretical analysis of this phenomena when it actually we give conditions to when it actually we can prove that it actually happens. But we see that in fact it's so strong that it happens even with very coarse kind of sampling of the space. So I'll show real examples. And we saw this behavior across different kinds of data transformations. It happens, it's a very strong thing. So getting back to the problem that we're really looking into, so we have a pair of images and we're given, our model is some transformation that maps the first image into the second one. In this case, we're going to work with homographies. And we're given a set of point matches. So those are matching interest points between pairs of matching interest points between the two images. So each match point M is a point Q1 in image 1, Q2 in image 2. And in this example, so you can see the true transformation. That's the one that maps image 1 to this pink quadrilateral. And we colored the matching points. The blue ones are inliers. The red ones are outliers. And this is a real example that we obtained by matching SIFT points. Okay, and in this case, like we had before, a point and a line, and the distance was the error. In this case, we define the error of a match M with respect to a transformation T. This is given down here below. So if we have the match Q1, Q2, Q1 and Q2, this is the match itself, and some transformation T. So the error is exactly this distance in the second image. And this is the standard thing that also RANSAC would work with. Okay, so now if we look at the ground truth transformation, we can look at each and one of the errors of the matches that we have. So say we have here 200 matching pairs. And say we sort these errors from the smallest to the largest. It's very interesting to look at the distribution of these errors. And this is what we do. This is just an illustration, but we plot here a curve which is the CDF of this distribution. So starting with match errors that are close to 0 down here, and the higher you let the match error go, you can accumulate up to 100% of the matches, and this is up here. Okay, so this is also a typical shape of this CDF. So there would be very few perfect matches. Even the inliers suffer from some noise. And usually you do see at a certain point this kind of plateau in the CDF, which kind of tells you that even if you let the match error grow significantly, you won't be finding any more matches. And this is usually the area of the true inlier rate. So just to compare RANSAC to our approach looking at this illustration, so what RANSAC does is it first assumes, or is given usually, an inlier threshold. So this is this point down here. And then it tries to find a transformation that maximizes the inlier rate with respect to this specific threshold. So it tries to find a transformation with as many as possible matches with up to this error. And if it succeeds, it will find a point that's at least at the height of this CDF. And you can run RANSAC with different thresholds. If you're more generous, give it a higher threshold, it would find a higher amount of inliers. Now, our approach really starts, as I said, with estimating the percentile of matches of interest. And then we find a transformation that minimizes the error with respect to that specific percentile of matches. Okay? So now back to this real result. This is what we get. So down here at the bottom, this blue curve is exactly the IRE measure that I was talking about. And on the y-axis, this is shown in log scale. So it's actually a very sharp minimum here. So in this example, we find a minimum at 30%, 37% of the matches. And once we have that, we can we look here. This is our search scheme that's for 37%. Finds a transformation with this amount of error. And you can see here also RANSAC results on this example. Okay, so this is basically the idea. So again, to talk about some prior work, so most methods tackle the consensus set maximization problem, which is given a definition of what it is to be an inlier, to find a model with maximal consensus, and RANSAC is the main technique used here. Starting from the original scheme, there have been, these are only a few of the many improvements and extensions there were over the years, which actually made it much more robust, made it run faster with different very good heuristics. And we will be looking at this recent work from PAMI 2013, which is called Universal RANSAC, which kind of incorporates all the good extensions that have been proposed over the years. It also comes with a very efficient source code, so we looked at that. And I should mention that there are, for this consensus set maximization problem, there are global optimization techniques. Some of them, so these are methods that actually guarantee that you find the global best transformation, the one that finds the real maximum number of inliers for a given threshold. But these methods are, they're interesting, but as you go higher up with the search space size, so like with homographies, they're not very practical. So now let me get into our method. So basically we have these three steps. We sample the homography space. Then using that, we estimate the inlier rate P star. And finally, having P star, we can find the best transformation for the specific P star. So how do we sample homography space? So I'll start with some definitions. So this, we've seen already, the error of a match M with respect to a transformation T, as I showed before, is this distance in the target image. Because we're now going to sample the space of transformations, the space of homography, so we need to define a distance between homographies or transformations. So what we use is this L infinity kind of distance, where if we have transformations T1 and T2, we go over all the points in image 1, and the distance is the maximal difference in the target locations in image 2. Okay, so this is an L infinity kind of distance between transformations. And one more thing, this is the Sampson error. It's the standard way of, so when you come up with, find some transformation, you don't only want to see how many inliers you have, you sometimes want to see how close it is to the ground truth transformation. So the Sampson error is the standard way of measuring this. So what you do is you take a large set of points, or maybe the entire set of points in image 1, and you map them with both the ground truth and your transformation T, and you take the average distance between the target locations in the second image. So this is the Sampson error. Okay, so
why not use the maximum just like before?
So the maximum kind of won't tell you the whole story of what the difference is like. The maximum we use because we are going to be using it to bound how much the error can change. It's kind of a worst case, to give worst case bounds on the change in the error. But in the end, you'd like to know over the whole image how close you are to the ground truth. So now, how do we sample the homography space? So we build this sampling that we call S epsilon. We have this precision parameter epsilon. And we do this, so if we're looking at images I1 and I2, we impose this two-dimensional grid of points over the space of image 2. So the diagonal distance here is epsilon. And the transformations that we allow are exactly the homographies that map the 4 corners of image I1 onto 4 points on this grid of points. So for example, you can see this green quadrilateral is a legal one because all the corners are on grid points. On the other hand, these 2 red ones are not, because they each have at least 1 corner that is not on a grid point. But on the other hand, there are in our sample transformations that are very close to these ones that are not in the sample. Okay, so here too. And formally what we get is an epsilon cover of the space of homographies. It means that any homography in the space has an epsilon close sample in this set that we constructed. Okay, and the main point that we get from this covering is that if we look at a single match between the 2 images, and we're looking at some transformation T, we ask ourselves what happens when you change the transformation to some neighboring transformation, to some other transformation whose corners are at most epsilon far. And what you easily get is that the error of the match, when you move between the two transformations, cannot change by more than epsilon. This is kind of trivial, but it's very important. And furthermore, if we don't only look at one match, but we look at all the matches, so we can look at different statistics of the matches, like the average of all the matches, a certain percentile, a mean of a certain quantile. All these measures will also change by at most epsilon when you move between these neighboring samples. So these facts are very important for us to give the guarantees on the error and to allow a branch and bound scheme that is fully guaranteed again. Okay. One other thing is that maybe a nice thing about this sampling is that it's rather uniform in the space of homographies. And when I say uniform, I mean uniform with respect to this distance between transformations that I define. So you can measure here also the cover radius and the packing radius of this cover, which are not very far apart. So, and this is important, for instance, when we have that IRE measure that we would like to measure in the continuous space. Since we do this through this sampling, we would like the sampling to be kind of uniform in space to represent what happens in the continuous space. Okay, so that was the sampling. Now, technically, how do we use this to estimate the inlier rate? So we're given a list of matches M. And we constructed this sampling of transformations S epsilon.
So you construct the complete, if there are m by n grid points, right? So mn grid points, you construct the 2 to the mn potential homographies?
Yes, but again, the idea will be to start with a very coarse sampling. So
okay.
Yeah, it does go to the power of 8 for homographies, like you have to choose each of the 4 corners.
Right, so it's 8 to the, well, right. Okay.
Yeah, it's the number of the points to, not really to, I mean, you want to make sure that it's a homography, and we kind of limit the scale of the homography, but up to that it grows.
Okay. Yep, okay.
Yeah. So we build this 2-dimensional matrix, error matrix E, where the entry ij is just the error of the match mi under the transformation tj. Okay, so you can think of maybe a couple of hundred of matches typically, and many thousands, or tens or hundreds of thousands of transformations. So we compute this matrix. Again, each row corresponds to a match, each column to a transformation. The first thing we do, for each column, we sort the errors in an ascending order. And what we get as a result is that if we look at a certain percentile, a row at a certain percentile p, we get the pth match error for each of the different transformations. So having that, we can now, for each such row of errors, we can find the minimal error. And we store this in this vector rmin. So rmin holds for each percentile the best possible error for that percentile over all different transformations. And now we can count in each such row how many of the errors are at most epsilon larger than the smallest error we found. So how many of the entries are at most epsilon larger than the minimal one we stored in rmin. And this is the IRE measure that I was talking about, that blue curve that we saw. And so we simply find the minimum of this vector, and the corresponding row is the percentile p star that we choose. Okay, so it's pretty simple. Now, once we did this, we can continue to find the best transformation for p star. So starting from the same point here, so this is giving a little more detail. So this is the row that we're working with. Say this was the best error we found, so we stored it here in rmin. And say in this example that there were 3 errors, so 1, 2, and 3, which were at most epsilon worse than the best one. And I marked with the red cross all the errors that were more than epsilon higher than the optimal one. So what we can do at this stage, and again, we have to keep in mind the construction of the sampling that we had. So one thing is that if we want to just return this transformation here that gave the best error, this transformation, we know that its error is at most epsilon higher than the optimal error in the continuous space. But what we actually do is we want to employ here a branch and bound scheme. So what we can show here is that we would like to improve the approximation to move to a finer sampling S epsilon half. And what we can safely do is any of these red transformations we can safely discard in a search space, because from this sampling we know that even if we open finer resolutions around this transformation, the error cannot change by more than epsilon, and therefore it cannot be even as good as this error that we already have. So what we do is we can focus on these three surviving transformations and open the finer sampling only around those. And we can repeat this in a branch and bound manner. Okay, so this is the idea. And now I'd like to relate back again to the this Inlier rate estimation measure. And really the two main insights were, so first we claim that this measure attains a minimum at the true Inlier rate P star. But another very interesting and practical fact is that, as we just saw, that the branch and bound scheme works best, the most efficiently, when it is given the true Inlier rate P star. And this, just going back here, so again, as a reminder, we chose the row to work with, the one with the minimal value here. And this vector, our IRE measure, is actually, it's a count of the number of surviving transformations for the branch and bound scheme. So, and if we look at this real example, again, this is log scale. If we chose a wrong, didn't work with this minimum point, but with a different point, the number of transformations that we had to open in the branch and bound scheme would be much worse. So it's a kind of a lucky situation here. Okay, so a lot of the paper tries to deal with understanding this this minimum phenomenon here, and we try to analyze this behavior and give some kind of analysis about why it happens. We did this making several different assumptions, which are very, I guess, there's a very large gap between what the setting that we're able to prove that this works compared to what we actually see in our experiments. So we believe that it's a much more general thing, but at the moment the proof is quite difficult even in a very limited setting. So what we do is, I'll just tell you about the basic idea. So we move to continuous spaces of transformations and matches. And we use a generative process for creating matches, under which we will analyze this measure. So what is this generative model? It's, I think, the standard way of thinking about this. How do we generate a single match M, which is a pair of points? In the background, we're given, we have some, the ground truth transformation T star, and we have some Inlier rate P star, and we're also working with an amount of noise R star, which we allow the Inlier matches to suffer from. So the Inlier matches also have some amount of noise, which is has a magnitude of R star. So for the moment, assume we take just an arbitrary point Q1 in the first image. So we can look at the target location in the second image. This would be where a perfect Inlier point Q2 would be. But what we actually do is we open a radius of r star around it, and with probability p star, we generate the point Q2 inside this circle as an inlier, and with probability 1 minus p star, it will be in the rest of the image. So this is the basic model, and it's kind of the standard way that, say, RANSAC papers generate synthetic examples. So this is what we have, and what we get is this kind of probability space in image 2 regarding where the location of the point Q2 will be. And then if we look at any transformation T where it maps Q1 to, we can look at a radius r around that point, and what we get here is, again, that if the point Q2 is within this red circle, the meaning is that the error of the match is at most r, and if it's outside, the error of the match is more than r. And we actually define, we look at probabilities here. We can look at the probability of the error of the match being at most r, and this is exactly the amount of the distribution in image I2 that this red circle captures. So this is what we'll be doing, and in our analysis, what we when we count transformations, what we do here is we actually count such red circles of a certain radius that capture a certain amount of the distribution. So this is how we analyze the measure. So again, the radiuses here correspond to match error thresholds, and probability here corresponds to, so if you generate many matches, what happens with a certain probability will happen at a certain percentile of the matches. So the assumptions we make here are, first of all, regarding the noise of inliers and both inliers and outliers. So an inlier is mapped into the green circle with uniform distribution, and an outlier is mapped to the rest of the image, again, uniformly. We think we can, regarding the inliers, we could use a Gaussian distribution around the center point, which is maybe more realistic. And what this allows us is to, when we look at any kind of area in the second image, to calculate the probability of a point landing in that area, we just have to measure areas inside the circle and outside the circle to get the probability. And also we assume only 2D translations, because this allows us not to assume anything about the distribution of the point Q1, but only focus in what happens in the second image. And what we end up getting is these equations that tie the IRE measure that we call here V with the different parameters, R star, P star, epsilon, and P. And what we do is we differentiate this function around P star to show that, that under certain conditions, a minimum does exist. So we're able to show, we can see here in this, this D-shaped area in the space of P star and R star, so the inlier rate and the inlier noise. In this whole D-shaped area, we show that the minimum must exist under these assumptions. So this is the theoretical analysis, and there are many details in the paper. Now I'd like to move to some experiments, some of the experiments that we did. So this is one of the experiments that tries to validate the IRE measure. And what I'm showing here is two extreme cases of this experiment. So it's a synthetic experiment. We generated point matches exactly according to the model that we defined. And what you can see here is, so images I1 and I2. This is a very extreme case in terms of the inlier rate, which is very low. It's P star is only 1% of the matches. So only the red matches here are inliers. The rest are random outliers. And the true model is the one that takes I1 to this black parallelogram. And here are the IRE measures that we obtain for this example. And you can see that for different values of epsilon, the minimum happens to be quite close to 1%, which is the true inlier rate. Again, this is another extreme example, and this one in the sense of the amount of noise that the inliers have, 8% of the image size, which is quite large. And you can see here again that the different curves of the IRE measure obtain a minimum around the true inlier rate, which is 16% in this example. Yeah?
Just to clarify, see if I understand, on the left side example, since P star is 1%, you were kind of bound to take a low R% because of the D shape, right? That you showed before?
Yeah.
Otherwise, it just wouldn't work, right?
Right. So, so these are two extreme cases. This one in terms of P star, and this one in terms of R star. If you take them both to be extremely low, we'll see real examples that are in that direction. But yeah.
Okay. And can I ask one more question?
Yeah.
You kind of alluded to the fact that you start with pretty coarse epsilon, and I kind of assume that you then do kind of a hierarchical or somehow, you know, use sequential epsilons which are lower in specific areas of the solution space, but I don't see how you do it.
So again, the branch and bound scheme is only in the second stage for finding the transformation. Basically, the estimation of the inlier rate P star is from the, we usually use the initial epsilon. Practically in some cases we do, maybe if we see that there isn't a clear minimum, we can try again with one finer epsilon, but we can't go much, refine epsilon too much because the sample grows a lot.
So epsilon is a guessy parameter.
So in this case, epsilon is not the sampling parameter, but it's the threshold of what we defined as a good transformation. It's the one that has the optimal error plus epsilon. So this is a synthetic example. We could still sample it very finely because it's 2D affine. But I'll show now the real results. On homographies, we worked with a very coarse epsilon. So this is now to move to the real data. We use these two data sets, the Mikolajczyk data set from Oxford and the pairs of images that come with the USAC method. So to talk about the runtime, it really depends on how well the branch and bound scheme works here. But typically, I'd say that it's around maybe 5 up to 10 seconds for an image pair. We haven't done much to improve this. It's quite a basic implementation. But again, the advantage is that it works on the full range of possible inlier rates and amounts of noise that the inliers suffer from, unlike RANSAC. And so this is what we have. And practically for homographies, so we do use an initial resolution of around epsilon of around 30% of the size, the dimension of image 2, which is extremely coarse. But still, we were able to find the inlier rate correctly in most cases, even with this very sparse resolution.
That's like a 3x3 grid?
So it's a bit more than 3 by 3 because we also have to take points outside the image because of scale, but say maybe 5 by 5, 6 by 6, but it still gives a huge number of transformations because it's homographies. But yeah, and we did do some very small changes to try to make things. So when you have a branch and bound scheme, there are many ways to do it correctly, efficiently. Some heuristics that can actually help you manage better the way that this tree expands. We added here a very degenerate kind of DFS search where we take the best current transformation and we just drill down locally. Hopefully it will increase the bound a little when we move to the next stage. There are better ways of doing this, but this is what we did at this stage. And also, once we find the final transformation, we can do this reweighted least squares optimization on the final set of inliers that we have, because even when you find the set of inliers, you would like to concentrate on the inliers that have a smaller amount of noise. So this is something that like low RANSAC does, so we have this as an option. And let's see some of the results. So these are real images from the USAC dataset. We have 3 pairs of images here. For each, in the middle column, you can see the inlier rate measure. Again, the y-axis is a log scale. You see the minimum, the minimums that we find here: 46% inliers, 36%, and in this case, 17%. And here you see the results overlaid on the ground truth CDF. So you can see RANSAC, USAC here, and our result.
How do you interpret these green curves with the red dashes when you say RANSAC results? These are RANSAC results for different inlier.
Right.
And
yeah.
So how do you tell if the algorithm's doing well? I mean, these are just number of matches, but presumably the homography that's estimated, right, could be very similar between doing 25 matches and 37 matches, right?
Right.
So what's significant here?
It is maybe quite confusing because even when you run RANSAC here, this is the standard threshold of RANSAC for SIFTs, 2 pixels of error. And you find this amount of inliers. If you use here 30 pixels of error, you find this amount of inliers, but actually most of these searches will find maybe the same transformation. Okay. Or a similar one. Just you count things here in a different way. So this doesn't really tell you how good the result is. It's just an interesting way of, you get an idea comparing to the ground truth CDF, but what I will show in the other data set is what the Sampson errors look like. Okay.
So, and what are the typical runtimes for the recommended USAC algorithm? So
USAC, it also there's no one runtime I could say, because they have these, they have ProSAC, which is one improvement, and LowSAC. So in some cases, standard RANSAC would have to evaluate, say, for a certain inlier rate, 50,000 transformations to kind of get a set of inliers. Right. But they have these heuristics where in some cases, like ProSAC, you rank the matches by their quality. Right. So sometimes they evaluate 10 transformations and find a perfect one. So it can take fractions, milliseconds to find the transformations. Okay. But in some cases, especially when the noise is higher and inlier rate is lower, it can take much longer and even fail. So that's what we see. So the more interesting data set, I think, is the Mikolajczyk one, because you have these 5 homography sequences. Each sequence has frames 1 to 6, and you can kind of see where, when the difficulty increases, where the methods still work. Till what stage they still work. So this, for example, is from one of the sequences, frames 1 and 2. So these sequences are mostly a viewpoint change. From frame 1 to 2, there's a slight viewpoint change. You can see, so there is the ground truth map. It's like a dashed thick green quadrilateral, and the pink quadrilateral is our result overlaid on that. So you can see that it looks right in this example. But again, this example, you can see that all the matches, I think 100% of them are inliers, because SIFT just worked very well here. So this was very easy. But as you go forward in this sequence, I hope you can see that the number of the percent of inliers drops drastically. And what you can't see, that even the inliers that you still have here also have a considerable amount of noise. So they're not localized Exactly, and we were kind of surprised because people think of SIFT as like you can control how much the localization error can be, but we found that it's much more than what people usually work with. So these are some other examples these are frames 1 and 4 from 3 of the different sequences. And again, the same kind of results that I showed before. And now if I move from frames 1 and 4 to frames 1 and 5, these are frames 1 and 5. So you can see that the inlier rates drop here. In this example, it's only 13% of inliers. And these are frames 1 and 6. Actually, this is one of the only examples that we totally failed. And this is due to the fact that there are only 2 correct matching SIFT points in this example. So SIFT totally broke down here. We couldn't do much. So really looking at these are the Sampson errors of both our method GMD and USAC. So we're looking at the 5 different sequences, and in each sequence, the 5 different image pair combinations. So you can see here the Sampson errors, which are in pixels. And if you look carefully, so in most cases, I think the methods are comparable. They do quite well. And I think even the ground truth transformation is maybe not, doesn't have sub-pixel accuracy. So being around 1 pixel error is, I think, just fine. But the interesting thing, I think, is looking at these 2 sequences where at a certain stage USAC fails earlier than we do. So in these 2 examples, we still managed to find a transformation which is not too bad compared to their failure. And just to look into these 2 examples, so now these are the 2 sequences, Graffiti and Graffiti 5. And we compare the 2 methods in terms of the inlier rate that they find and the amount of noise that these inliers have. So this is just an example. But the 2 cases where they failed and we still succeeded, you can see that they're very extreme, both in terms of P star, which is only 12% and 9% here, and also the inlier noise, which is kind of related to R star. So this R star is also very high here, so 8.5 with standard deviation of 14, and this example too. And down at the bottom here, we can see for these 2 sequences, again, the ground truth CDFs of the errors with our result overlaid on each one of them. So you have frames, the red one is frames 1, 2, frames 1, 3, and so on. So these 2 difficult examples are this one down here and this one here, where you see that if you look at the CDF, there are very few errors that have very few matches that have an error that's below, say, even 10 pixels. So these examples are really very challenging, and we still manage to get a result.
The USAC epsilon was higher than that error?
Yeah, we ran USAC with like in different steps of thresholds up to I think 40 or 50. But the problem with USAC, so again, I think it's a mistake in the basic analysis of RANSAC, where you assume there are inliers a certain amount, and your only goal is to manage to randomly pick a set of points that are purely inliers. But what happens if, and I showed an example before, that the set of inliers that you pick still has some amount of noise. You're not guaranteed using that to find, if the amount of noise in the inliers is high, you won't always find the true model. So I think this is what happens in these 2 examples here.
Right, whereas you don't have to find a minimal set. You can just find the inliers and then do a least squares or weighted least squares.
Yeah, yeah, that's what we do. Okay, so I think I'm done with that. I'd like to say just a few words about the fast match work. how different it is compared to this one. So just in a couple of words, because I think it's interesting. So so there, the problem looks very similar because you're trying to search in transformation space, mapping the first image into the second one. So we worked with affine transformations, but we actually generalized it to homographies, just like we have here. So it looks very similar, but what is very different is the error function that you work with. So this was a pure kind of geometric problem because you work only with locations of these matches. And in template matching, you work with the pixels, the pixel intensities themselves. So we work with the sum of absolute differences of when you map the template into the image, you take each pixel and look at the difference to the target pixel it's mapped to. So again, we have this idea of sampling the space, but and things are much simpler because we don't have this, we didn't handle this outlier problem that we had here. So we consider all the pixels in the template as inliers. We're working with the whole, with everything. So in that sense, it's much easier than this example. But on the other hand, so when we had this sampling we worked with here, and the main point was that when you move between neighboring samples, the error does not change by more than epsilon. That was very easy was trivial to get here. But what happens when you do that with sum of absolute differences? It's not true. So even if you change your transformation by 1 pixel, the error can go anywhere. So we don't have that guarantee. But what we did manage to do there is to show that when you change your transformation, the error can actually not change arbitrarily, but it can change as a function of how much the transformation is different, and also depending on the smoothness of the template. So it turns out that the smoother the template is, or the image is, the change in the error is much smaller, and the more textured the template is, the error can change in a faster manner. So we managed to prove there exactly bounds on this relation on how much the error can change as a function of the change in transformation and the smoothness of the template. And based on that, we can determine the exact density of the sample of transformations that we use. And we have the same kind of guarantees there. So we do the same branch and bound scheme, and we manage to get results. I'll just show, I'll skip these, but sorry. So these are kind of results that we get. This is an image. We extract a random template and then search for it back inside the image. And it works very well. These are examples with kind of a large template with respect to the image, but we looked at different size templates going down to very small dimensions of templates. And what we show so we compare our method to a interest point based method like a SIFT based matching method, and it turns out that really the smaller the templates are, you can see that feature based methods just break down. So when you work with small templates, like these are 25% of the image size here, they're just shown larger, but actually this is where it comes from. So this is 25% in these examples, 15%, and so on. We go down even to 10% of the image. So you can see that when you take templates of this size, it's almost impossible to think of trying to match feature points between the two images. So actually, I don't know of any other way to tackle this problem, especially as the templates get smaller. So I think it's a very effective method for doing that.
What about scaling between the template and the image?
Scaling?
Do you assume that there is scaling, and how far can you?
So again, we worked in this setting. We worked with affine transformations, and we limit the scale to say up to times 3 and 1 over 3. So yeah, you have to limit your search space in some way, but still it manages to do things quite quickly. Here you can see one more special thing that we use here, that instead of computing when you map the template into each of the thousands of locations in the image, because you're willing to suffer this approximation of, say, epsilon, so you can only, instead of mapping the entire set of pixels, you can only choose a random, set of pixels and evaluate the error only on those and get the same kind of guarantees. So we look at actually a constant number of pixels in the template size. It doesn't depend on the size of the template, and evaluate the error only on those specific, you can see these pixels here. So this really, together with a branch and bound, enables to speed up the whole thing, and it works quite nicely. So just to summarize now, so these are some other examples. We believe that some different large spaces, search spaces, can be exhaustively searched through if you have an understanding on the behavior of the error function. And if you do so you get global guarantees on an approximation, and you can then usually also use a branch and bound scheme to get a very good approximation. So really, there are other domains that we're already looking at applying this technique, and also the robust estimation with the inlier rate error measure. We think would be interesting to look at other domains, like in even machine learning, where you specifically want to take into account the fact that there are inliers and outliers that you'd like to totally reject, and not just use some robust measures that can limit how much they can ruin your results, but actually work with try to isolate the inliers of the problem. So we're thinking in those directions too. That's all, I think. Any questions?
Nice work. Do you have, will there be an implementation that you can play with?
So there will be. For all my works, there ends up being an implementation available. For most of them there is. This latest one with the inlier rate is not available yet, but hopefully in a couple of months. Yeah.
When you're looking through the space of affine transformations, you said, for instance, that you will eliminate scales beyond 3x and 1 over 3x.
Yeah.
Are there? Could you have kind of say probabilistic priors on the affine transformations, and would that help at all if you knew which ones were more likely to look at before others?
So like
let's say like a 1x scaling is twice as likely as a 2x scaling, for instance. Right? You can imagine the distribution.
So I would imagine how you could do things to get your result faster, but in terms of if you still want to keep the guarantee on the global search, so probably not. But practically, yeah, I guess that you would prefer to sample more densely to start with in the areas that are more likely. So.
Estimating the rate of inliers, if someone gave you, if you started to check with some guesses which are close to the minimum, you will find it faster, right? And then you could maybe order the branch and bound according to what expect to see.
So I'm not sure I exactly get how that can be done, but I think that so one of the things is that we do the inlier rate estimation first, only at the first level, and then continue with that. Mm-hmm. There should be a way of kind of running things together. So like maybe from the first level getting a coarse idea of what the inlier rate is, and then also refining that, moving to the next stages. So possibly that could be done.
Great. Thanks.
Okay, thank you.